All right, we're going to look now at a technique called logarithmic differentiation. Logarithmic differentiation is something that's useful for exponential functions when the variable is in the exponent, but it's also particularly useful when you have the variable in both the exponent and the base, that kind of a function. Essentially what this technique involves is taking the natural logarithm of both sides and then differentiating implicitly. What that allows to happen here is if you take the natural logarithm of both sides, then it allows you to get at that exponent because you can use the power rule for exponents, and that can go right in front there. And so you're going to have ln of y equals x ln x. So now you've turned that exponential thing into a product, and we can differentiate implicitly. All right, so let me rewrite this. And if we are going to take the derivative of both sides, then what we're going to end up with here, because that product on that side, on the left side what we're going to end up with is we have a natural logarithm function here, and the derivative of that is 1 over that variable, except for this is not just an x here, so we got to use the chain rule here. So this is going to be multiplied by dy dx or y prime, whichever notation you're happy using. On the right, it's a product, so we got to make sure to use the product rule. So we're going to have x prime times ln x plus x times ln x prime, or in other words, 1 times ln x plus x times 1 over x. We simplify that a little bit. We have ln x plus 1, right? Because this thing, x times 1 over x is 1. We had still on the other side 1 over y times y prime. If we want to isolate y prime, because that's what we're trying to do, we're trying to find the derivative here, we can multiply both sides by y, and we're going to get y prime is y times ln x plus 1. And that's the derivative, but it's nice if we can express the derivative in terms of x alone over here. So we want to change this y. We're going to replace that y with something we know it's equal to, and actually right in the beginning we know what it's equal to. It's equal to x to the x. So we're going to use that substitution, and we're going to write this as y prime equals x to the x times ln x plus 1. Now you could expand this out if you wanted to, if that was more useful for what you're going to do with it, but this is just fine as is. All right, so that's a quick look at logarithmic differentiation, something you can use with exponential functions, and particularly when you have variables in both the base and the exponent.